over many of these things. What's the resource of Web3? Well, I'm not sure if there is just one resource. You could argue that storage, like this decentralized availability, would also constitute a resource. But certainly the main resource of Web3 is block space. Essentially, what is block space? Well, it's computation, right? And to some extent, storage. Well, my computer does computation. Does that mean it has block space? No. Crucially, block space is decentralized or resilient to computation. It's computation that cannot be altered by any particular economic force. Right? And the more that the more secure it is, the less that it can realistically be altered, the more Web3 it is. You kind of measure this, the quality of this block space in a few different ways. I'll talk about that in a second. But the crucial thing is, it's really just computation. It's really just the thing that a computer provides me. It's just that it's resilient. It's resilient against the economic forces of the world that we assume, because it's a Web3 system, are ultimately going to be, from the perspective of the Web3 system, malevolent. Now, Polkadot is designed to create that highest quality block space. Right? That's why we're here. Right? We're not cutting corners. We're going through. So, one of the ways that we can measure it is by computational throughput, data throughput. Now, transactions per second is a sort of it's a very imperfect way of measuring computational and data throughput of a system. Because transactions, it turns out, require both data and computation to be processed. Unfortunately, different systems process transactions in different ways. Indeed, different systems have completely different definitions of what constitutes a transaction. These transactions are the sort of proper transactions. They're like, and by proper I mean they operate on an state that is independent of the other transactions that are happening at roughly the same time. They always include a signature, one per transaction. They always include a transfer, one per transaction. Sometimes we find TPS metrics that do not uphold these three things, and then that's where some systems have floating. In fact, some systems don't even require a transfer time at all. As you can see, the number is substantially greater than any other system that is actually deployed. Of course, some systems claim theoretical throughput numbers. Other systems say that they have some particular deployed testnet behind closed doors. Whatever. This is for actually deployed live decentralized systems. Polkadot has the highest bandwidth, right? So we just take data bandwidth alone, ignore processing, computation. It's still far higher than other data availability systems, other systems that are domain specific for data availability. In terms of the decentralization or the number of economic actors that will have to collude or be hacked or be malicious before the system breaks, Polkadot has by far the highest. Right? This is by far the most decentralized system of anything that's handling any significant amount of things. Ethereum, despite its efforts to decentralize through having lots and lots of validator keys, actually, I think this Nakamoto coefficient of the number of independent economic actors that have to collude to break the system is only about 2 or 3. And it turns out that Polkadot is the most energy efficient of the major chains. Right? And there's a reason that it's energy efficient. Essentially, it comes down to scaling out, not scaling out. That's what I want to talk about for the rest of this. The way that it achieves this vast amounts of processing throughput, vast amounts of data availability in time, in part, is parallelization, essentially distributing work over its node network rather than trying to get all of the nodes to replicate each other. It also enjoys, it doesn't do this at the cost of tearing apart the network into separate, separately secured, sort of independent sovereign networks. that would be a problematic approach. That would essentially divide and conquer not the problem, but the solution, which is its economic integrity. Polkadot also, in order to create rich interoperability between its sort of separate portions of the system, really needed and pioneered interoperability. One of the things that we created and released was XCM, cross-consensus messaging program, that really attempted to create a common format for actions allowing interoperation to function. And of course, it has substantial data, very large and effective data availability system. All right, that's Polkadot. I want to talk now about JAM. So JAM is the next, the Polkadot governance essentially gave JAM the carte blanche permission to be the next Polkadot protocol. This was voted on by quite a lot of people, and essentially now has been specified as, in a decentralized fashion, as the upgrade path for Polkadot. It's got a formal specification, the grey paper. For Polkadot, it means increasing performance quite substantially and preparing it to become more in line with this concept of being a web cloud platform. There's a lot of people implementing that. So the grey paper is kind of, I actually released the grey paper 10 years, almost to the day, out by warranty, from the day that I launched the yellow paper back in 2014. That was sort of on purpose. The grey paper and the yellow paper are kind of similar in that they utilize similar formalisms and have a similar structure. The grey paper describes a more sophisticated system, obviously, as we learn more about engineering decentralized computers. They do tend to become a little bit more sophisticated. It's actually not that much bigger than the yellow paper at present. The yellow paper is about 55 pages. The grey paper is a little more, it's about 60, 65. So but they're definitely of comparable size. The grey paper is probably a little bit more complex in how all of the different pieces interact with each other. But it's not like a million miles away in terms of how difficult it is. By having a grey paper, by having a technical, formal specification of the protocol, essentially by launching the protocol before we launch any piece of software that implements the protocol, we try to create an environment of diversity so that others can also implement this software. I'm happy to say there's quite a few people around the world that have taken up this challenge and are busy implementing this protocol specification. Of course, I have my own implementation that's sort of sitting behind the scenes. I mean, I work on it, of course, with a team as well, a few other people. But this is not meant to be any sort of reference implementation. This is just another implementation. The reference is the great. That's the thing that is public now. It's very, hopefully, unambiguous. In addition to the paper attempting to create an environment for people to implement JAM, there's also a fairly substantial prize pool for anyone who wants to implement it and who thinks that they have the ability. It's 10 million DOT, which is still quite a lot of money. It's actually sort of split up into different sort of smaller prize pools that are earmarked for particular computer languages, sets of them. 35 teams that we know about. I think there are probably one or two others that we don't know about, who are independent, totally independent, right? Really, like nothing to do with, as far as I know, certainly nothing to do with me, nothing to do with parity, nothing to do with Web3 Foundation, are currently implementing this protocol. And they're using between them 15 programs. Now, in addition to making when we when we try and get lots and lots of teams, lots and lots of people who are not in the same organization, to implement a protocol that's only specified by essentially, mathematical formalisms, we run the risk of when we get to actual instantiation of the network, actually trying to bring this thing to life, it not really measuring up to expectations, simply because there will be, the whole point of JAM and of generally decentralized peer-to-peer systems is that we're counting on the emergent effects of the system. It's not like where, if we're just having a sort of regular server-client architecture, where we're counting on the direct effects of the server. Yeah. We can literally engineer all the effects that we want directly in the server, and everything that we engineer will work exactly as we write it. That's what we want. So it's like, I have this problem, I need to have web pages served. Then I will make a piece of software that serves web pages, right? And then it runs on a server and it serves web pages. And you can very clearly link the problem, or rather what it is that you want to happen, with the solution, which is how I actually make it happen, right? Those two things are basically one-to-one mapping. What I want to happen, how I make it. I just use a computer program. Unfortunately, with peer-to-peer systems, with actually decentralized, proper, crypto-economic systems, the two things are not linked anymore. What we're counting on is the emergent effect. The direct effect of a node is kind of useless. It's the emergent effect of 1,000 different nodes all interacting with each other that creates the system, creates the final thing that is what I want to happen, which is a distributed, decentralized computer. One node on its own doesn't give me that. And so this is about attempting to engineer this emergent effect. Now, we have some very clever minds working on this, and it's, we have confidence that this is what the emergent effect will be. But it's hard to do it unless to debug. Debugging emergent effects is really difficult, because your debugger works at the level below the actual effect. So it doesn't give you exactly what you want. You can't debug it directly. You can only debug the things that are sort of working together to individually. Yeah. Essentially, what you want is the forest, but you can only inspect an individual tree. So having access to all of the trees in one place, ideally amalgamating all of that information again into a single place, is really useful. We can't do this on a live system. Yeah, we can't do it because it's decentralized. We'd have to get literally all, first we have to know all the validators, and then we'd have to get them all to send us all of their logs and log them into one place and hope that all their time blocks were synchronized. It would be a mess, and it wouldn't be weatherproof, and it wouldn't be resilient. If any one person knows all the validators, that's kind of a potentially compromising piece of information. So instead, we create a testing and experimentation facility that has all of the computational power that is required by the network to operate, but instead hosts it in a single place with a high-power logging system. Essentially, we create a scale model, and it's with this that we can actually do our experimentation, optimization, and see the whole forest all at once, not have to inspect a few trees here and there. And that's what the JAM toaster is. It's not a supercomputer by today's supercomputer standards, but it's certainly no slouch. It's got 16,500 thread-ripple cores, and these things go pretty quick, and an awful lot of RAM, 32 terabytes. So it's it's capable of doing the level of computation that we would need to actually simulate the whole JAM. Good. So I've talked around JAM quite a lot. I'm gonna talk around it a bit more, but I hope I'm slowly zeroing in on what it is and what it's about. So what is JAM? I did a little picture of that. It looks a bit like a flower. So let's go back to the driving factors. I mentioned this in a slide a few bits back with what is what. These are how I like to think in terms of these. So first and foremost, resilience. The first Web3 system, Bitcoin, the reason it was a Web3 system is because it's resilient. The others are all kind of nice to haves. The less you have them, the less useful the system is. But resilience is crucial. If it's not resilient, it's fragile, then it's not Web3. It's just a regular system. Our Bitcoin is obviously quite resilient because it's been around for so long, right? What's it, 17 years? So it's like, that's a pretty good indication that it's resilient. Bitcoin didn't have some of these other things. It's not very general. You can't do that much on it. It's kind of good for what it is, but it doesn't do much else. And it's not very performant. Now, when we, the key sort of move forward, key sort of innovation that Ethereum provided over Bitcoin was introducing this concept of generality. It made it more general. Didn't make it perfectly general. As I said, it's not actually Turing complete, but it does have a scripting language that lets you write and execute a lot more interesting software than Bitcoin required. Ethereum wasn't performant. Now, when we got to Polkadot sort of provided all three, and it was like, oh, right, job done, easy, because I didn't realize that there were two other things that might work. It turns out that coherency, which is something that Polkadot sacrificed to get performance, is an important attribute. It's perhaps not as important. I think it's not as important as performance. Elements, the individual blockchains that exist with Polkadot are themselves coherent. But that aside, coherency is something that we would want in an ideal world, and obviously accessibility too. We want as many people to use it as possible. So, specifically, past one, Ethereum 1. Well, I've drawn it as this is my little drawing. Take it for what it is. Not very scalable. Now, it turns out some people, just to explain the drawing, the dotted line on the outside is like the consensus. Right? So it's like everyone has consensus. And then the thick line on the inside is the state. Right? So there's the single state. It's not very scalable. You can't, it's sort of like a cold-blooded creature. It's like there's a limit to how big it can grow, like physical limit to how big it can grow. This is actually an important consideration we'll go into in a second. People did try to scale this model, right? Call this high-performance synchron, so kind of just scale that version of Ethereum. We saw different networks trying to do this in different ways. And they've, over the last 10 years, right, we've seen various different attempts at essentially just trying to make Ethereum go faster. Generally, these things are either centralizing or fragile, they break a lot, or both. And ultimately, they're still going to hit this ceiling. Right? Ultimately, the ceiling is just how fast can you make a single computer work, like how many transactions can a single computer process. That's the sort of end game of this. The end game of centralization is running all on one machine. And the end game of scalability, therefore, is, well, how fast can that machine keep up? If we don't have to worry about like replicating it across the world to potentially other machines that might not be as fast and might not have as fast a link. But even if we do try to replicate it across and actually keep the centralization, we're not going to be able to scale, because then we're going to have not only, it will only go with the slowest machine that's expected to keep up, but also we have the problem of replicating state, right? It's like as slow as that machine can keep up, but also as slow as you can like synchronize with all the other machines sending data out and receiving data back. These systems are not scalable. And we know that Silicon Valley has a mantra: scale out, not up, right? You can't expect this to work. It's just a bad direction to go. So what are the other directions that we've got? Well, one of them is the one that sort of Cosmos used. We said, all right, we're not going to try and scale up. We'll try and have multiple different instances of chains. But then in order for them to interrupt, otherwise we just end up with tons of different systems that are not compatible. So actually we're going to build bridges, which was a big deal. So there's a bridge, and they have a consensus mechanism, Tendermint, which is very highly sort of easy to make bridges. The problem with this is, of course, that each of the networks has its own security, has its own economic backing, its own capital backing. which means the network as a whole, if you expect causal interoperability between the networks, this is the thing that you actually want, will end up being only as secure as the weakest participant. You're essentially opening your doors to other potentially compromised systems. Now, something that came up is these are now different systems. These different chains are different systems. They each have their own state. They each have their own list of accounts. They each have their own smart contracts, right? They each do their own things. And to interoperate with something inside of the same chain as you is easy and fast and cheap, as it would be if it was all just a single system. But to operate with something in a different chain becomes expensive, and slow, and difficult, because it's in a totally different system. It's kind of like, you can very easily, if I want to set up a bar, and I want to get some beer, right? Well, I really like British beer. Yeah. So British beer is it's sort of fermented, but it still has the bacteria, which means it takes time to happen, and then once it's ready, it lasts for maybe 5 weeks. Yeah, and you have to keep refrigerated at all times. This means if I'm opening a bar in the UK where the beer is brewed, then it's relatively easy, right? No problem. I just find a brewery, and I say I want some beer from you, and they deliver it every week or two. All good. If I'm in Japan opening a bar, it's a problem. Yeah. Now at that point, I have to have I can maybe put it on a boat, but that boat might take longer than 5 weeks to arrive. By the time the beer arrives, it's not so nice anymore. Maybe I put it on a plane. Now it's super expensive. Maybe I try and put it on as like spare capacity in planes, and then sort of pay a bit less. But then maybe it doesn't get there on time, and then it's bad again. It's problematic. Yeah. And this is the issue. If we have different systems, different states, and we partition our states up in this way, it's really hard for us to have full interoperability. It turns out also make it like engineering a new blockchain, it's kind of hard compared to just engineering a smart contract. Raising the barriers to entry. Okay, what about Ethereum post, like, I don't know, 2029, or Ethereum including its L2 rollups? Well, the different rollups tend to, so if you're not familiar, rollups are essentially ways of compressing correctness, right? So you can take a piece of computation that would normally take quite a long time to do, like for example, validating a block, and you can compress that computation into a much smaller piece of computation that demonstrates beyond reasonable doubt that the ramifications of that computation. And this is the basis for in some sense, at least it was until a month or two back, scaling Ethereum. Problem is that different approaches tend to have different trade-offs. Some approaches are what we call optimistic rollups, or ZK rollups, and the different providers of these rollups kind of want some sort of USP. They want something that they do better than the other ones. So they'll often try to differentiate themselves, as you would if you were a business competing in the market. And what we end up with is this kind of patchwork quilt, where it's kind of you don't really get the same thing from the different rollups. Some might take ages before any effects on the rollup can actually take effect outside of the rollup. And if in some cases we end up with actually different security parameters. Many of the rollups are highly centralized. They have either a specific set of validators, they have very few validators, or they have a single agent who is generating proofs, allowing the possibility of stalling the chain on demand or censoring. But even more pointedly, we still suffer from this persistent state partition. The different rollups are different areas of state. Interacting within a rollup is generally cheap and fast and easy. Interacting between rollups is generally expensive, slow, and Hogarop provides essentially a homogeneous rollup environment. So the different blockchains can kind of do their thing, but the actual means of compressing their computation is the same mechanism, which means that we get